Pythagoras Theorem. In a right-angled triangle, two sides are at right angle to each other, and the third side opposite to the right angle is called hypotenuse. The relation between these sides was established by a very famous Greek mathematician, Pythagoras. This theorem is perhaps one of the oldest theorems known and used by ancient civilizations. Pythagoras theorem can be proved by various methods. Here, we are going to use the properties of similarity in right-angled triangles studied earlier. One. The theorem gives the relation between the sides of a right-angled triangle. It states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the remaining two sides. To prove the theorem, we will use the property of similarity of right-angled triangles. It is given in triangle ABC, angle ABC is equal to 90 degrees. We have to prove that AC squared is equal to AB squared plus BC squared. Let us draw segment BD perpendicular to hypotenuse AC, such that point D lies between points A and C. Proof. In triangle ABC, segment BD is perpendicular to hypotenuse AC by construction. Therefore, by similarity of right-angled triangles, triangle ABC is similar to triangle ADB. The corresponding sides of similar triangles are in proportion. Therefore, AB upon AD is equal to AC upon AB. That is, AB squared is equal to AC into AD. Similarly, triangle ABC and triangle BDC are similar, and BC upon DC is equal to AC upon BC, corresponding sides of similar triangles. By cross-multiplying, we get BC squared is equal to AC into DC. Now adding both the statements, we get AB squared plus BC squared is equal to AC into AD plus AC into DC. Therefore, AB squared plus BC squared is equal to AC into bracket AD plus DC, since D is between points A and C. Therefore, AB squared plus BC squared is equal to AC squared. Hence, the theorem is proved. Let us see now how Pythagoras theorem is useful in solving problems. Look at this problem. Example. A ladder 10 meters long reaches a window 8 meters above the ground. Find the distance of the foot of the ladder from the base of the wall. For solving this problem, first, draw a figure representing the given data. Triangle ABC is a right-angled triangle in which AB is the height of the window from the ground. AC is the ladder and BC is the distance of the foot of the ladder from the base of the wall. By applying Pythagoras theorem, we get AC squared is equal to AB squared plus BC squared. Substituting AB equal to 8 and AC equal to 10, we get 10 squared is equal to 8 squared plus BC squared. After solving, we get BC is equal to 6. Therefore, the distance between the foot of the ladder and the base of the wall is 6 meters. Pythagorean triplets. There is one interesting fact you all would like to know. One day, When Pythagoras was drawing in the sand with a stick, he found that if he drew the squares on the sides of a right-angled triangle with sides 3, 4, and 5, the area of the larger square was equal to the sum of the areas of two smaller squares. He tried this with different right-angled triangles and found this true with them also. Thus, the set of numbers such as 3, 4, 5, 6, 8, 10, 9, 12, 15 came to be known as Pythagorean triplets. Let's learn some of these triplets and with the help of them determine whether the given triangles are right-angled triangles. Example. Here, the sides of some triangles are given. We have to determine which of them are right-angled triangles. The first set is 8, 15, 17. To determine if these are the sides of a right-angled triangle, we will take the sum of the squares of two smaller sides and see whether it is equal to the square of the larger side. So, 8 squared plus 15 squared is equal to 64 plus 225, which is equal to 289. The square of 17 is 289. Therefore, 8, 15 and 17 are the sides of a right-angled triangle. Now let's check on the next set of sides, which is 11, 12 and 15. 11 squared plus 12 squared is equal to 121 plus 144. That is equal to 265. Square of 15 is 225. It is clear from the answers that 11 squared plus 12 squared is not equal to 15 squared. Therefore, the triangle with sides 11, 12 and 15 is not a right-angled triangle. Four. Converse of Pythagoras Theorem. We will study the converse of Pythagoras Theorem now. In a triangle, if the square of one side is equal to the sum of the squares of the remaining two sides, then the angle opposite to the first side is a right angle. It is given that in triangle ABC, AC squared is equal to AB squared plus BC squared. We have to prove that angle B is a right angle, or, in other words, triangle ABC is a right-angled triangle. Let us do a construction. Draw triangle PQR such that QR is equal to BC, PQ is equal to AB, and angle Q is equal to 90 degrees. Proof. In triangle PQR, angle Q is equal to 90 degrees by construction. Therefore, by Pythagoras theorem, PR squared is equal to PQ squared plus QR squared. But by construction, PQ is equal to AB and QR is equal to BC. Therefore, PR squared is equal to AB squared plus BC squared. It is given AC squared is equal to AB squared plus BC squared. Therefore, PR squared is equal to AC squared, that is PR is equal to AC. Now, in triangle ABC and triangle PQR, AB is equal to PQ and BC is equal to QR by construction. We have already proved that AC is equal to PR. Therefore, by SSS test of congruency of triangles, triangle ABC is congruent to triangle PQR. Therefore, angle ABC is congruent to angle PQR, corresponding angles of congruent triangles. But Angle PQR is 90 degree by construction. Therefore, angle ABC is equal to 90 degrees. That is, triangle ABC is a right-angled triangle. Converse of Pythagoras theorem is used to determine whether the given triangles are right-angled triangles. Example: the sides of a triangle are 40, 20, and 30. Determine whether the triangle is a right-angled triangle. By converse of Pythagoras theorem, if the square of one side of a triangle is equal to the sum of squares of remaining two sides, then the triangle is a right-angled triangle. So let's find the squares of all the three sides and see if the sum of squares of any two sides is equal to the third side. The square of 20 is 400, that of 30 is 900, and the square of 40 is 1600. We find 400 plus 900 is not equal to 1600. Hence, the given triangle is not a right-angled triangle. Now we will take another set of values. Example: here, the sides of the triangle are 11, 60, and 61. State whether the given triangle is a right-angled triangle or not. Let's follow the same method we used for the first example. So the square of 11 is 121. The square of 60 is 3600 and the square of 61 is 3721. If we add 121 to 3600, the sum is equal to 3721, which is the square of the third side. As the sum of squares of two sides is equal to the square of the third side, by converse of Pythagoras theorem, the given triangle is a right-angled triangle. It's time for an activity now. Draw a right-angled triangle on a graph paper. Construct squares on each of these sides. Draw a perpendicular line onto the hypotenuse from the vertex of the right angle. Extend it to intersect the opposite side of the square formed on the hypotenuse. Color square BGFC and rectangle MCEN with yellow color and color square AJHB and rectangle ADNM with blue color. Measure the areas of square BGFC and rectangle MCEN. What do you find? The areas of both these figures are equal. Also, measure the areas of square AJHB and rectangle ADNM. What do you find here? Even here, in this case, both the areas are equal. Now, if we add the areas of both the squares and compare with the sum of areas of two rectangles, we will find area of square AJHB plus area of square BGFC is equal to area of rectangle ADNM plus area of rectangle MCEN. Is it not interesting to know that this is the Euclidean proof for Pythagoras theorem? Proof of Pythagoras theorem by Indian mathematician Bhaskaracharya. The theorem known to us as Pythagoras theorem was also known to Indian, Greek, Chinese, and Babylonian mathematicians even before Pythagoras. The eminent Indian mathematician of 2nd century AD, Bhaskaracharya, gave the proof for Pythagoras theorem. Now, we will discuss the proof given by him. He used the diagram shown here. He gave the proof by using the property of similarity. Have a look at the proof. In the figure 1, you can see a square with side C. Inside the square, you will see 4 right-angled triangles and a square. Areas of these 4 right-angled triangles with base A and height B are equal to 4 into half AB. Area of the square with side B minus A is equal to B minus A bracket squared. Area of the square with side C is equal to the sum of areas of triangles and area of small square. Thus, C squared is equal to 4 into half AB plus into bracket B minus A, the bracket squared. By solving, we get C squared is equal to B squared plus A squared. It's time to practice what we have learned so far. We will solve a few problems based on Pythagoras theorem. Example. In this problem, we have to prove that the sum of the squares of the sides of a rhombus is equal to the sum of the squares of its diagonals. It is given that quadrilateral ABCD is a rhombus. AC and BD are the diagonals intersecting each other at point O. We have to prove that AB squared plus BC squared plus CD squared plus AD squared is equal to AC squared plus BD squared. That is, 4AB squared is equal to AC squared plus BD squared, as all the 4 sides of a rhombus are equal. Proof. We know that the diagonals of a rhombus bisect each other at right angle. Therefore, AO is equal to half AC and BO is equal to half BD. Also, angle AOB is equal to 90 degrees. In triangle AOB, by Pythagoras theorem, AO squared plus BO squared is equal to AB squared. That is, half AC the bracket squared plus half BD the bracket squared is equal to AB squared. By solving, we get 4AB squared is equal to AC squared plus BD squared. The next one is, prove that 3 times the square of any side of an equilateral triangle is equal to 4 times the square of an altitude. So we have equilateral triangle ABC, in which AB equals BC equals AC and AD is the altitude of triangle ABC. We have to prove 3 into AB squared is equal to 4 into AD squared. Proof. In equilateral triangle ABC, AD is perpendicular to BC. Therefore, triangle ABD is a right-angled triangle. By Pythagoras theorem, AB squared is equal to BD squared plus AD squared. That is, AB squared equal to half BC the whole squared plus AD squared, which is equal to half AB the whole squared plus AD squared, since AB is equal to BC. By solving, we get 3 into AB squared is equal to 4 into AD squared. We will solve one more problem. ABC is a triangle in which AB is equal to AC and D is any point on BC. Prove that AB squared minus AD squared is equal to BD into CD. In triangle ABC, it is given that AB is equal to AC, that is, triangle ABC is an isosceles triangle. D is any point on BC. We have to prove that AB squared minus AD squared is equal to BD into CD. Here, we will do a construction. Draw AE perpendicular to side BC. Proof. In triangle ABD, AE is perpendicular to BE by construction. Therefore, triangle ABE is a right-angled triangle. Therefore, by Pythagoras theorem, AB squared is equal to BE squared plus AE squared. Similarly, in right-angled triangle ADE, AD squared is equal to DE squared plus AE squared. Subtracting AD squared from AB squared, we get AB squared minus AD squared is equal to BE squared plus AE squared minus in the bracket DE squared plus AE squared. After solving and factorizing, we get AB squared minus AD squared is equal to into bracket BE minus DE into bracket BE plus DE. But BE minus DE is equal to BD, since point D lies between points B and E. Therefore, AB squared minus AD squared is equal to BD into bracket BE plus DE. But we know in isosceles triangle ABC, AE is perpendicular to base BC, therefore bisects BC. Hence, BE equals to CE. Substituting BE by CE, we get AB squared minus AD squared is equal to BD into bracket CE plus DE. Point E lies between points D and C. Hence, CE plus DE is equal to CD. Thus, we get AB squared minus AD squared is equal to BD into CD.